Thank you very much for your patience. This is our last talk for today, but do hang around for the closing at the end, which is only just a minute or two. There'll be a party at Verity Lane behind Reload Bar tonight at 7 p.m. The buses leave at 6:15 p.m. And in fact, Paul organised the buses, so thanks very much to Paul for getting us to Verity Lane in a nice and easy manner. There are two loops actually of the buses, so if you don't catch the first set of buses, there's 3 buses coming at a time. Just hang around and there's a second round of buses as well. The CTF will close down for the night at 5:30 p.m. and resume again tomorrow at 9. For the IR challenge, continue working on it overnight and see how you go. Right now we have one of our hosts and staff for the Hardware Hacking Village doing a talk on micro-architectural attacks and reflecting on 45 years of research since a note on the confinement problem. So let's welcome Paul Harvey to the stage.
Thanks for waiting. My technology isn't very happy today. I'm a electronics person who largely didn't find much work doing electronics in Australia, so I do software for most of my career. I do open source stuff, usually with open software, open source, and this talk is kind of, you know, we flock from the next shiny thing, from one next shiny thing to the next, and this is sort of just taking a few minutes to reflect on where we've come from, what are the problems that we're solving, and where are we going next? How can you tell if you're going in circles if you don't know where you've come from? So today it's mostly a sort of haze of PDFs and a lot of PDFs. It's not really original research what I'm showing here, it's just some stuff that I thought is interesting. Side channel attacks and micro-architectural attacks, turn out they go back a long way. How many of us here today would put your hand up if you think you're a builder or you work more on making stuff than breaking stuff? Yeah, a few of us. We sort of, I think as builders, we kind of get comfortable in where we are in our stack. I know some of us pretend that we're full stack. I don't even know what that means. Like, I don't know what cloud means really, or agile. And it's interesting to think about abstraction layers. There are some really great works on talking about how to classify vulnerabilities and what properties each kinds of vulnerability in a classification system have. And an interesting one is Bishop from 1999 here. He talks about the confusion that there is in traditional taxonomies for bugs. It's hard to put bugs into one bug. This was back in the 90s, of course. So one of the observations he found was where you are in the abstraction layers counts for context when you're thinking about bugs. This next paper, Holographic Vulnerabilities, it's talking about data flows across interface boundaries and across abstraction layers, and they're able to express most bugs in these terms, they think. I don't necessarily agree with all of these papers, by the way. They're just talking about interesting stuff. So the Halvard down the bottom there said it simply, and it's basically insecurity lives and breathes in the cracks between abstraction layers. This is a graph from one of the papers that my talk is focusing on the hardware stuff, obviously. This is a plot of a portion of my papers database. If you don't use a papers database program, I highly recommend Zotero. It's pretty cool. There's something called the MASCAB, the Micro-Architectural Attacks Side Channel Attack Bibliography, and it has 137 references going back to 1974. There's an additional 100-ish items that are in there, and this top pane is showing about 16 years worth of research. It's been pretty busy since the year 2000. Just for some context, back in the 1960s, computers cost the best part of $20 million in 2017 money. And IBM had a relationship with MIT that they would get a newish model of mainframe as they became available, because MIT were good at putting them to work and finding, fun stuff to do with them, and that helped develop their business. One of the interesting things about this, though, was IBM demanded some control of these donated machines. And one of the example jobs that they had to run at the drop of a hat was the IBM CEO's yacht handicapping program. So when he was figuring out what handicaps the yachts in the yacht races should have, they had to stop this $20 million machine and make it run the CEO's job, and then they could go back to doing real work. And coping with that context switch, changing jobs midstream, because these were batch machines, they're sort of glorified graphics calculators, that wasn't quite a refined thing at that time. And I'll just talk about in a minute what really enabled multi-user, the having more than one thing running at a time on a machine. This switching to the CEO's job and back kind of had it sort of accelerated the development at MIT for getting context switching going, basically. And they had context switching on the order of minutes to hours, but it was possible. You could interrupt a job and restore it when you came back, and that was a big deal at the time. So 72 years ago, some World War II electrical engineers said, let there be batch programming. And things kind of weren't very friendly for a long time. These were big, scary machines. You needed expensive operators to run them. In 1941, the Germans made the Z3. In 1944, the US Navy made the Mark I. And the ENIAC, which is the public first computer, non-classified computer, was 1946. And CIRAC was 1949. In those years, VI was 30 years away. So there was no good text editors any time soon. So they started dreaming about time sharing and not having to have one person at a time. And this man, John Backus, he's like the B in BNF, if you know what that is, Backus normal form. Oh, sorry. CTSS was the compatible time-sharing system. This was a precursor to something called Multics. How many of you have heard of Multics? Ah, good. It turns out Multics made a big mark on computer security at the time, and CTSS was a precursor, and they sort of bootstrapped Multics with CTSS. And they were dreaming about this multi-user stuff for a good long while before they actually got it. John McCarthy, who invented Lisp, of course, actually started butchering one of these very expensive machines, an IBM 704, to have interrupts. So the IBM 704 they had didn't have interrupts, and that made the possibility of developing time sharing very difficult. So he sort of was pulling it apart and soldering in relays and valves and stuff, and it made IBM moderately upset because it was technically a leased machine. And in the end, they convinced them to sell a customization option that Boeing had for real-time work with wind tunnels. And that actually had an interrupt feature that was actually not an official sort of catalog item, but it was something that IBM had developed for Boeing, and they were able to use it. And the 704 ran off valves. So the first transistorized machine was actually the 7090, which is what Multics ran on. Sorry, it was a transistorized machine. Multics started at the outset to securely run multiple users' data control data access in a really tight way that could satisfy government requirements, not from the very beginning, but very soon after its beginnings. The US government wanted to do this as sort of, I think, as a cost-saving exercise. Because the machines were so expensive, they wanted a way to share the resources between different classification levels and different compartments within classification levels. And they eventually did achieve the Orange Book B2 rating, which took a very long time, and then they killed it shortly after it achieved certification, which is a bit tragic. So they learnt some things from this. Security through obscurity doesn't work. Also, counting on attackers to be lazy doesn't work. Penetrate and patch doesn't work. This was like in 1970, they'd figured that out. Security has to be formally defined relative to a policy model, and they need implementations that are formally verified. And formal verification techniques were developed at the time. We had IBM's Vienna development method, and there was also the Z proof checker. So they had this proof checking, like really advanced stuff that's sort of coming back into vogue a little bit now with functional programming. It has its origins back in the 70s. This is one of my favorite slides. Has anyone heard of the Ware report? No one? Yes, one person? The Ware report was 1970, and they were thinking about, as you can see in the picture here, all the different kinds of threats on shared computers. In this next slides, I have stuff from DoD's Computer Security Initiative program. These were seminars held in the aftermath of Multics, kind of, and the other efforts they had. Multics wasn't the only one, but we don't have time to talk about the others today. They spent a lot of money, a staggering amount of money, hundreds of millions of dollars, trying to get secure systems, and they didn't want to keep doing that forever. So they really wanted to try and get the private sector on board for building secure systems and maybe get some off-the-shelf secure stuff one day. Wouldn't that be nice? They're still waiting, I think. But some of the stuff they were thinking about was, as you can see, the CPU features. By the way, hackers, Technicolor Rainbow stuff. Incidentally, Hackers was released in 1995. Common Criteria version 1 was published for drafts in January 1996. Just thought I'd throw that out there. There's something called the program status word in IBM 360 mainframes, and this is kind of interesting. They talk about a key which protects programs, it protects the memory manager, the MMU, from being able to access memory when you're in the context of a given program. It's kind of, it feels a little bit like Intel MPX, or maybe with the Multics hardware, actually, they had cross-ring pointed reference checks. So if a lower privileged domain tried to dereference a pointer that was minted in a more privileged ring, that would generate a fault, which kind of reminds me a little bit about ARM authenticated pointers. It's not really the same thing, but so we had some admissions here in 1979 about the fact that they weren't really achieving the outcomes they wanted. They had to revert to traditional techniques, and traditional techniques for maintaining security isolation back then was basically turn off the giant mainframe, plug in some different hard drives, and start the next shift for the next classification level if you wanted to do that. But I think the other thing that was happening at that time was Multics was from the 60s, and it was solving a 60s problem. By the time the 70s had come around, computers were getting, not ridiculously cheap, but they were cheap enough that you could have one in each office, and they didn't really have such an urgent need to spend hundreds of millions of dollars to get secure isolation between users. You could just buy another PDP and another PDP machine, and just buy more hardware and solve it that way. Some examples of penetrations that they experienced back in the early 70s. OS 360 had supervisor calls that were not adequately protected. There was GCOS, checkpoint dumps, not restricted. I think that's kind of like a core dump, but imagine it's world readable, and that would be bad. This one down the bottom here, misuse of I/O processor. That's kind of like your modern day DMA attacks. They had different little CPUs off to the side of these big things to speed up I/O, and you could program them with additional software. Okay. So the lessons learned. Unfortunately, something horrible has happened. So I'll just wing it. A note on the confinement problem was pretty cool. 1973, they found side channels where you could have notionally different isolated processors sharing information between each other using IPC. Files in home directories. These seem kind of obvious now, but they weren't really thinking about things systematically sometimes when the end users were putting together their information systems. Exfiltration via billing info was really exciting. They thought, like, if they're billing by the minute of how much CPU or what utilization the hardware has, you could modulate the load on the system to sort of get some data exfil out through your invoices. Probably a low bit rate. And of course, this one here, varying its ratio. Processors can virtually monitor the system load and communicate that way. So we have this one from 1995, leaks via registers when context switching. So this is stuff like the segment registers weren't often cleaned up in those days when things like Windows were running. The FPU is kind of difficult to sanitize. Every time you context switch, it's kind of expensive, so you can leak some information. If the FPU is in an exception state, you can do some timing analysis there to communicate between processors. High-resolution timers are a common thing throughout the literature, back to the 70s as well. And I'll get to that one. So I find it really interesting that Firefox in 2015 had a vulnerability from the Spy in the Sandbox paper, which was about using high-resolution timers as part of its exploitation with branch prediction stuff. So they reduced the resolution down to 5 microseconds. But then in 2018, when the Spectre meltdown attacks happened, they just had to reduce the resolution down to 2 milliseconds. I don't know how to pronounce the first author's name here, so that's kind of embarrassing, but he writes some really good stuff, and this is kind of it was studying branch predictors and branch target buffers as a way of using for side channels initially, but then his team found that they could also spy on another process by polluting the branch target buffer with sort of like a cache purge and reload attack, where they can sort of spy on the state of the branch target buffers and determine which code paths the other process was taking. It looks really fiddly to me, but these guys figured it out in 2006. And then a subsequent paper, he really figured it out because he was able to extract RSA secret keys just by spying on a single operation. In the last mile, they actually measured branch mispredicts as a side channel, 1100 bits per second. Timing attacks. We've known about them for a long time now. They seem old hat, but in 1996, I don't know if this was the actual first paper, but it is a very early paper on using timing side channels at all for extracting secret key information. Rowhammer is a good one we're probably all familiar with, so I won't spend too much time on it, but basically it involves repeatedly accessing a given row of memory, which the memory controller will happily top up with charge with the normal scheduled recharge cycles. Unfortunately, it drains the neighbor rows as well when you're accessing the same memory address over and over again. It'll drain the neighbor rows charge to such an extent that it will, and they're not on the refresh schedule, basically. So you can flip bits by doing that. And there is a paper on doing this with NAND flash in SSDs as well, so you can sort of flip bits selectively. But I haven't put an actual paper there because I haven't seen one that actually pulls off an attack successfully. But maybe there is one, so please do feel free to tweet me if you know of one. Corkscrew is really fun because it's basically failure to identify the power management in a system as part of your trusted computing base. TCB is something that security analysts often think about because you need to be able to trust your TCB. It's everything that the CPU and your environment has to be able to trust in order to execute code safely. And what they're able to do is have an unprivileged process manipulate the voltage and affecting the CPU scaling in a Nexus 6, I think it is, such that they can glitch the CPU. So when it's in a very sensitive part of some crypto, so they're actually able to extract AES keys, not directly, but they're able to, there's a lot of learning phase happening, so when they map out exactly what the timings should be, they can target the final round of AES. AES has 10 rounds, I think. So or is it 8 rounds? So on the second final round, they glitch that round and then compare the result with. So it's like a known plain text attack. So they know what the result should have been from the trusted zone encryption process, but they get a corrupted one back by glitching that final AES round, and they're able to use a cryptanalysis attack with 2 to the 12, which is pretty fast. And they're also able to get the trusted zone in the Nexus 6 to load some self-signed code, which it shouldn't be able to do. Another category of attack is the non-deterministic timing in stuff that we don't normally think about. So this one's like using SVG canvas, I think, to put a filter on bits of the DOM that a piece of JavaScript shouldn't have privileges to be able to manipulate. So like if it's an iframe in a web browser, it shouldn't be able to access the parent DOM's DOM nodes, but it can map out what color the pixels are by putting an SVG filter over them and timing the differences, because it goes into the FPU, and FPUs are pretty noisy when it comes to doing graphical stuff. So this is just another paper I wanted to share because it's indicative of just how complex x86 is getting. This single instruction has so many modes and states that, and features that we can get a Turing machine out of this one instruction. You actually don't have to use other instructions. There's a compiler called Mobfuscator. If I had my speaker notes, I'd be a lot more eloquent, I promise. But to top that off, the page fault weird machine is probably my favorite. It doesn't actually successfully execute any instructions. This is just using the MMU to continuously trap and set up page faults in a way that does useful computation. And there's a C compiler for that as well. And I imagine debugging that would be a nightmare. It's called TrapCC. When Meltdown Inspector was going on at the start of the year, this guy on Twitter I thought was interesting. He said he gave a talk at Intel with this slide. And he was trying to say to Intel, it is very likely that out-of-order execution, prefetches, intermediate buffers, dependence predictors, memory controllers, energy management units, value predictors, all this stuff could lead to attacks not just on cryptography implementations, but non-cryptography applications as well. And he was completely right. So he actually gave Intel this presentation 6 years ago. It obviously wasn't in a part of Intel that could do anything with that information, of course. So the conclusions are, if you need to share anything with an attacker, that's just really hard. If you don't have to, don't. Obviously, not everyone can afford to do that. In the physical realm, you know, we can limit so it's kind of terrifying that a JavaScript program from an ad can break out and maybe get all the way up to bare metal. So just turn on all the things, secure boot especially. In the virtual realm, there's dedicated hosting offerings and bare metal offerings. I think Packet.net is one such vendor. And if we don't have to trust CPUs, then just use the TPMs and HSMs we have available. There's smart cards as well. They're all standards-based. They're a nightmare to work with, but they're worth using. That's all. Thank you.
Paul. Do we have any questions in the audience? Great. We'll just give some housekeeping about where to go tonight. So the buses to the Verity Lane party will come at 6:15. There'll be 2 rounds of buses, like I said earlier. There is a small passing storm currently going on. not to our annoyance, but apparently it is only going to be quite quick, and it will pass fairly quickly and smoothly. So even though it seems like a tornado is going on outside at the moment, give it 15 minutes or half an hour and it should be okay. That's pretty much it. Thanks for attending the first day. I hope you all enjoyed it. And we'll see you tomorrow. We'll see you at the party. Thank you very much.